Okay, we can start. A little bit low in numbers, but still more than half of the class is here. So recall that we have a rule that when half of the class is not here, I'll take attendance quiz for 10 points. But attendance, we have 35 registered students, so it should be 16, 17 to qualify for that. Okay. So today you're more than that. Before we start, do you have any questions? Anything you want to ask about the course, about things we're doing? Okay, so the plan today is we'll do 1 more hour of this number theory, but we'll have some word problems, which we'll use Euclidean algorithm. I also would like to talk about prime numbers and how you can sort of send secret information using prime numbers. And it's not going to be a very high level cipher mathematics, but it's just still something that you may like to talk about. Probably we'll finish this before 2 hours, so we'll start the next section, which is about counting. So we'll start talking about permutations, combinations at some point today. Okay, let's start with this question. This is something I advertised before that you can use number theory to try to answer. So Griffin has 2 containers. One container holds 13 ounces and the other holds 55 ounces. Question is, can Griffin measure exactly 1 ounce using these 2 containers? If so, explain how. We talked about this possibility of using number theory for solving questions like this. I actually wrote some questions on the board probably at the beginning of number theory about a week ago. And that question, somebody was able to say exactly what the combination is right away. So here too, maybe you can get lucky and say, okay, I can get 1 ounce using 3 times 13 and 2 times 55 or something. But we'll learn a more sort of formal way of how to do it each time. So,
One is the greatest common divisor of these 2, and the linear combination of these 2. The number that can be written with the linear combination of these 2 is the 1. So we need to.
But how do you know? How do you know you can write the greatest common divisor as using these numbers?
If we just talk on the proof that,
you can prove that. Can we find? So the discussion we're having is basically, if you know that greatest common divisor, if you know that greatest common divisor of 2 numbers is D, my pens, then there exist integers x and y such that d is equal to ax plus by. This is what the claim is. That if we knew the greatest common divisor is 1, our friend, your name? Murat says that you can write 1 as something times 13 plus 55 times something by some numbers, integers. And now you can use these integers to explain how you can measure 1 ounce using these 13 and 55. So for example, these numbers will be, so in this case, what we are claiming is that we'll get 1 is equal to 13 times some integer, 55 times another integer. They can be negative potentially. So it will say that use like 13 ounce container x times, and then use 55 ounce one y times to add and subtract and so on to get 1 ounce. So, and then I challenge him, how do you know you can find this x and y?
If you know an integer that can divide a and b both, for example, c and d, that divides d also.
So d is the greatest common divisor a and b, so d should divide a and b. We know that.
D should be divided by c also.
Okay.
Then if a is divided by c and b is divided by c, d is also divided by c.
Yes. But how do you know you can write d as ax plus by? I mean, that is the thing. I'm not sure. Let's cheat first. Suppose there is no theory. Can we get clever about this? So how you can get clever about something? Suppose you play with numbers and try to find 1 as combination of these two. So what makes this 1 special is the greatest common divisor. So let's see if we can play with this. So how you find that 1 is greatest common divisor? One of the ways was using Euclidean algorithm, right? And how did it work? We took the big number, divide the small number. And then we keep doing some process. So let's do that process to see 1. So how many times 55 includes 13? 3 or 4? 4 times. You get 52. You get 3. And the process is that you carry the 13. Now you divide it to the remainder. So 4 times. And now you carry this, you divide with the remainder. As soon as you get 0, the number before is the greatest common divisor. Okay, that was the process. Can you in any way use this division sequence of divisions to write 1 as a combination of 55 and 30?
All remainders are the linear combination of the previous divisor and the
So suggestion is, because we have this division relation, this gives us equations. So 3 is actually a combination of 55 and 13 from this division relation. Similarly, 1 is a linear combination of 3 and 13. So the special numbers are these numbers. The rest is just coefficients. So think about this. 1 is a combination of 3 and 13. But 3 is a combination of 13 and 55. You combine this to get 1 as a combination of 13 and 55. Let me show you how you do it. So you say 1 is equal to 13 minus 3 times 4. You can actually write it as 4 times 3. So this is a combination of 4 and 13 and 3. You write 1 as combination of 13 and linear combination of 13 and 4. Now, use the previous equation to write 3 as a combination of 13 and 5, 55, by writing it from that equation like this. So I just carried 3 from that equation. So I get 55 minus 4 times 13. Put these together, you get minus 4 times 55. This is your special number. Plus 16 plus 1, 17 times 13. So that means you can get 1 as 17 times 13 minus 4 times 55. That means if you use 13 container with 13 ounce, 17 times to fill something, and then 4 times using the 55 container to take out the water, the remaining water will be 1 ounce. Depending on the situation, you may have to do it slightly differently, but this is like if you have a big pole, you can use these 13 and 55 to get 1 ounce using these numbers. So this proves that you have actually a way of writing D in any case you face in terms of those two numbers, A and B. Let me write one more question. I mean, this is something that every year I try to teach because this shows how like interesting things you can obtain using something like greatest common divisors. Another example, this is from the book as well. Assisting students in programming classes. Brian, these names doesn't mean anything. We can change them, of course. This is from Grimaldi. So Brian finds that on the average, he can help a student debug a Java program in 6 minutes. But it takes 10 minutes to debug a program written in C++. If he works continuously, for 104 minutes and doesn't waste any time, it's probably not possible, but it's still assumption. How many programs can he debug? we could have just written the numbers 6 and 10, but part of this course is to understand these problems in the story problem sense, that if given a story, you should be able to take out some of the numbers that's important in the story and then write the question in your own way and then solve it using the techniques you know and so on. So reading and understanding stories is part of the course. That's why I keep writing them. So this Brian, this student, assistant of the students, uses 6 minutes for Java. So debugs Java in 6 minutes. And then 10 minutes, these are the important things, in C++. So there are 2 different program types, languages. One is 6, the other is 10. And then he works totally 104 minutes. How many programs he debugs on each language? That's what we need to know. So it's this kind of problem. So we should be able, we should use the same technique. We want to find some x and y and so on. So solution, we need to find x and y such that you get 104 programs, 10, this is 104 minutes, 10 minutes for each of the x, 6. So this is the number of C++ programs. And this is the number of Java programs. So this is the number of times Brian debugs C++ and the other is number of times debugs Java programs. The catch is he cannot do negative this time. Okay, that's a very important part of this question. The other problem, you can sort of take water out. So there's some sort of, you can do negatives, right? Here, they have to be positive. You can allow to do no work. You can maybe not do any debugging on a Java program, but you can't do negative work, right? You can't do negative work. So that's a little bit harder and more strange question than other one. Because it could happen that we get some negative numbers in that process I explained to you. So you have to sort of adjust your answer. So how do we start? We want to get 104. So we want to know first greatest common divisor of 10 and 6, right? So what's the greatest common divisor of 10 and 6? What's the biggest number divides both? 2. And then I can probably write 10 as linear combination 10 and 6. You can use Euclidean algorithm for that, or you can directly even write it, right? So with the Euclidean algorithm, this is how you do it. 6 is 1 time. You get 4. 6 divided by 4. You get 4. You get 2. So this is your greatest common divisor. So it tells you that 10 is equal to 6. 1 times 6 plus 4. In this case, it's actually relatively easy to write. So 4, and then the second sentence says 6 is equal to 1 times 4 plus 2. So you want to write 2 in terms of 10 and 6. So that means 2 is equal to 6 minus 4 from this equation. And now you want to get rid of 4. 4 is 10 minus 6. So you get minus 110 plus, you get 1, 1, 2. You can see that 2 times 6 is 12. minus 10 is 2. So that's the linear combination you get. As we were afraid, you got negative numbers. So what do you do to get rid of this? How do you find x and y? Any ideas? So how do I find this x and y using this? Any ideas? Think about it. Let me write it again. So we know that 2 is equal to minus 1 times 10 plus 2 times 6. So I want to make this positive, these numbers, coefficients positive. So how can I approach to this?
You add a number which is divided by 6 and 10.
So if I add 6 times 10 on this side and 10 times 6 on this side, they will cancel each other. So if I, we have to first go to the 104, sorry. Yeah, in this case, you can't do really much. I mean, you're stuck with 2. But we're trying to do it with 104, which will give us more room. So let's multiply it with 52 first. So you get 104. Now we can talk about it. So with 52, you get these numbers. Okay. So we want to write 104, not 2. Okay. 2 is just we got the greatest common divisor. But we want to write 104 with combination of that. So we just multiply with 52. Okay. Now 104 is minus 52 times 10, 104 times 6. Right? And this is negative. We don't want this to be negative. And the idea is that if you add 6 times something here and subtract 10 times something here, you still have 104 as total. Okay? So if you add this to here to make this a little bit more, and then subtract something from here to make this, you still have 104. The answer doesn't change. And you can do it a couple of times. You can do it k times. K times 60 minus k times 60, if you add this to equation, you still have the same thing. And k is any number you choose. Okay? So what it tells you that if you put 6k minus 52 for any k as your coefficient, and then 104 times minus 10k as any coefficient here, you still get 104. And now you're free to choose different k's. Okay? You can choose any integer actually. Z is the integer, so any integer. So why should I choose k to make both of them positive? Like k1 wouldn't do it, right? Because it's only changing by 6, so it's still negative. 10 is possible, because you get 60 minus 52, 8, a positive number here. And you get 104 minus 100, 4. That's a positive number. So you want both of them to be positive. So we want this. And you see that here you need at least 10. Here you can't do anything more than 10, because this is 100, is the maximum you can put to stay positive. So the only possibility is 10. 9 does it? Yes. Sorry. It's number of times you debug the program. Sorry, that's true. Yes. So instead of multiples of, you're right here. Sorry. So the suggestion is why play with 6 and 10 when they have a greatest common divisor 2, right? So you can change it like saying 3 and 5. Now k is positive, but okay. I'm sure. Okay, let's see. It's not quite the same thing. Let's put the 3 and 5. Okay. So now you're allowed to use 20 or 18, but you're also allowed to use 19. Right? You can use anything. So 20 will do it, 18 does it, right? 60, but 19 also do it. So now you get one more possibility. But so with 20, you get 60 minus 2. So this is the Java, and this is the C++. No, this is the, so this X is C++. This is the Java. So this is your X, this is your Y number. So we found that X is 3k minus 15, and k is possibly 18 and 19 or 20. So for 20, you get 60 minus 52 is 8. So you do 8 times C++. And then you get totally 80. And then for the same 20, you get 4. 4 times Java. And 12. So 80 plus 12, 24. 104. So the total becomes, so this is 8 times 10, 4 times 6, 80 plus 24, you get 104. So this is a good combination. You could do 8 times C++, 4 times Java, you'll spend in total of 104 minutes. What you get for 19, can you see? 19 times 3 is 57? No, 58? 57? What's 3 times 19? Huh? 57, right? 30 plus 27, 57. Minus 52 is 5. So it's actually just 3 less. So 5 times C++, and then 19 times 5 is 85, right? 95. So 104 minus 95, 9. So 9 times Java. So you can do 5 times C++, 9 times Java. And then you get 50 minutes spent on C++. And 9 times 6, 54 minutes for this. Totally 104 minutes again. And then for 18, you get 2 minutes, 2 Java programs, and here 14 minutes for Java, 2 minutes for C++. Again, this is 20 minutes for this. 14 times 6 is 84. 84 plus 20 is 104. So they all give you 104 minutes. And these are positive numbers that makes this. Only 3 of the positive number pairs that does it. If you if you go to case 17, this becomes negative, or K21, this becomes negative. So you can see that the increments actually by plus 5 on this side, and here it's by plus 3. Okay. So there are more than one possible way of spending our time with different debugging. Here we use the fact that greatest common divisor is actually 2, so we divide by 2 both of the numbers to get combinations like that. Any questions? We almost missed the number, so thank you. There's actually a theorem which says that the fact that you can write greatest common divisor is a linear combination of A and B formally can be proved. There's a statement. We call statements either theorems or propositions. I think this is a theorem in the book so let A and B are positive integers. Then greatest common divisor of A and B is actually equal to smallest positive number of the form positive integer of the form ax plus by. Not only it can be written as ax plus by, but it is the smallest positive integer you can obtain using this A and B. So it's the smallest positive you can get using these combinations. So that's why you can do it. I mean, we have been doing it using Euclidean algorithm, but you can actually do it because of this theorem. You can see that it's always possible to write it. Okay? And now you have to adjust it to get different numbers, positive numbers sometimes. Okay, we will finish number theory with one last thing to discuss. It's called prime numbers. Okay. There's lots of very nice, we call it beautiful mathematics around prime numbers. There's lots of hard open questions, but also prime numbers are building blocks for a lot of internet security and ciphering systems. So it's not only interest for mathematicians nowadays, it's interest for every engineers as well. So let me say what they are, and then we can talk about how you can use them. So a prime number is a number that cannot be divided by anything except itself and 1. Okay? So there's a positive number, a positive integer, p bigger than 1 is called a prime number. If only divisors of p are 1 and p. So if there is nothing else divided as integer, positive integer bigger than 1, you call it a prime number. So what's the smallest prime number? Can you tell me? 2. What's the next one? 3. Next one? 5. Next one? So we get 2, 3, 4 is not, 5, 6 is not, 7. 6 is not because it's divided by 3 and 2, right? So you can start listing numbers and then crossing out the ones which are not. So like between 7, it's not true that every odd number is prime, right? Because you can have 9 which is divided by 3. So you can actually, this is called the C method. This is, you can sort of use this method of crossing out to understand what primes are. Okay, so you can actually find all the numbers which are prime in small range. There's computer programs which you can use to check if something is not divisible by anything else or not. The first thing you may want to ask, after a while you start crossing so many numbers that they may stop to exist. Like maybe there are no big prime numbers after 1 million. So maybe there are only finite many of them. Do you know if there are finite many prime numbers or infinite many of them? Do they stop to exist after a while? Huh? You have to prove it. So how many people knows if there are finite many or infinite many primes? Finite many? Raise your hand. Infinite many? Okay, so we know there are infinite many. How many people knows why? 1, 2, okay. There's actually a very simple argument why there are infinite many primes. So this is, there are infinite many primes. There is no limit to number of prime numbers. I can give you a proof. I don't know if in the proof let's assume something and then we give a proof. There's a theorem called fundamental theorem of arithmetic. Which basically you can use to argue this, but so every this is relatively easy to prove. This is usually proved in math classes, like in number theory courses you prove this. It's stated in our book as a section. There's a section in Grimaldi dealing with the fundamental theorem. But something that intuitively you know that all the numbers you can write either they're themselves not divisible by anything, but if they're divisible by something, you can start writing as product of things. And then when you write it as product of things, eventually you end up with writing it product of things that can't be written as product of smaller things. The smallest piece you get is a prime number. Like you can start with 120, for example. You say 120 is 2 times something, right? It's 2 times 60. But then I can say this is 4 times 15. But I know 15 is also written as 3 times 5. And then 4, I can write it as 2 times 2. So you end up with like keep writing pieces as product of smaller pieces. And when this process stops, it stops exactly when all of the numbers in the product are things you can write as product of 2 things. If you can write a number as product of 2 things, that's a prime number. So that's why prime numbers are your building blocks for numbers in terms of multiplication. They're like atoms of number theory. Everything we know about numbers some way related to prime numbers. So it's important to know exactly understand prime numbers and talk about them.
But in terms of multiplication?
Huh? Yes. So addition is, we think, relatively better understood. That's why. So let me write a very short proof for this infinite prime number theorem. So any ideas how to do it? Some of you probably seen this, but there's a very, very elegant proof that I can fit just here. And anyone can understand. It's a very, very, one of the most beautiful results or beautiful proofs. So the argument is like this. Suppose there are finitely many primes. Then you can list them, right? There are first prime, second prime, list them. There will be some n of them. N is some number. Okay? Let be all the primes we have, all the primes. There is only, say, n of them, and there only this much. If you had like only 153 primes, you say this is the first prime, this is the second prime. You can list them, right, into a list. So you'll have exactly this many primes. Then, look at, take their product, multiply them. Multiply all the primes you know. 3, 2, we know all these primes, right? So multiply them. You get a finite number. Okay? Add 1 to that number. You get another finite number. So you have a number now. Okay? And it is a number. Every number is either prime or is a product of primes. So you should be able to write this number as product of primes. Right? But what are the primes? These are the primes, right? So suppose P1 divisors, or Pi. So let's call this number M. Pi divides M. You multiply all of them, you added 1, you get something. You're saying that it has to be divided by these primes, right? So suppose Pi, one of them, divides M. What will happen?
It will not be a prime number.
It will divide M, but then it is in this list, right? So it divides this number too. If it divides this number and this number, it should divide their difference. which is 1. So that conclusion is a ridiculous conclusion. A prime number cannot divide 1. They're much bigger than 1. Because of that, you cannot have finite many primes. This is all. That's why it's called beautiful proof. It's very elegant. If you had this many, you can make a number that no longer will be divided by any of these numbers. That will be a problem. Okay? Let's see how I'm doing. Okay, 2 minutes. Let me direct you to something. 2 things we had discussed last time. I mean, we are doing these things sometimes from Sheldon's book and sometimes from Grimaldi. And in Grimaldi, Greatest Common Divisors, section 4.4. So we have done that. And 4.5 is the fundamental theorem of arithmetic. So we have that. So these 2 sections we have done. Just to finish, we'll take a break. When we come back, I will explain how you can use prime numbers to make ciphers, to make the securing communication between different parties. So there is quite a bit interesting things you can use for this. Another note, for the greatest common divisor, somebody asked before how fast the Euclid's algorithm goes. There is a computation of its complexity of the Euclid's algorithm, but it's much later in the book. It's in the recurrence relation section on page 488. If you know recurrence relations a little bit, you can read this. Complexity. It's very nice. It's very nice computation. It basically says that if you have A and B to calculate this greatest common divisor, use this Euclidean algorithm, right? You keep dividing. The bigger number, say, is A. Look at the number A and count the number of digits. Your division algorithm, your Euclid's algorithm, will finish less than 5 times the number of digits in A. So it will always be less than 5 times the number of digits. So if you're using Euclid's division for, say, numbers with 3 digits, you cannot do more than 15 divisions. That's the theorem. And it's very relatively easy argument. And it's called Lame's theorem. But I will not do it because I will have to do a lot of... It comes from Fibonacci sequences. So we have to discuss Fibonacci sequences if you want to understand. But if you're curious, that's Lame's theorem. And it's 5 times the number of digits is the upper bound for number of divisions you have to do in Euclid's theorem. And there's things like that. I mean, these are in the book, comes back again and again. Lame is lame. So maybe once we do the recurrence, if we get time, we could go back to this and look at it. But the estimate is 5 times the number of digits is the upper bound. Okay, let's take a 10-minute break and continue.